Hi, everyone, and welcome to the fourth and final lesson in Module 10. And this module, or this lesson is going to be focused on titrations. Now, typically in a normal year, we would do this and then we would have a big lab on titrations, and it's fun and everybody has a great time. But now you'll just have to do the simulation that's been posted. For those of you who are interested and plan to take my class again next year, we will definitely do at least 2 or 3 titrations. So you will still get to do them, so don't worry. So what is a titration? Titration is the process of adding a reactant from a burette to neutralize another reactant, either an indicator or using either an indicator or data device to signal the equivalence point. So we've got, in this example here, we've got the Erlenmeyer flask with the acid in it and a indicator. The indicator that we use is called phenolphthalein. It starts out colorless, I was going to say clear, colorless, and then as you add the base, it turns a pink color. Okay, and you add the base you add the base slowly from the burette so that you can figure out how much of the base you use in order to determine the concentration of the acid. And it says that we do this until we get to the equivalence point, and it's the point at the very moment when neutralization has occurred. So at the equivalence point, the moles of acid is equal to the moles of base because they're trying to neutralize, cancel each other out, okay? You can do, like I said, a titration with an indicator, which would be the color change, or you can do a titration with a pH probe, and then you'll get what's referred to as a titration curve, which is that thing right there with pH on the Y, volume added on the X. As you add, you increase the pH. In this example, I'm starting with an acid, and I'm adding base because the pH is going up. You can see there's a steady but slow increase in pH until it zooms up. And basically, it zooms up. Where it zooms up, about the middle part of that is your equivalence point. Okay. Here's some important information. pH is equal to pKa. Half the equivalence point, and pKa is equal to the negative log of the Ka. Okay. So how do we calculate when we're doing titrations? The titration calculation, MAVA is equal to MBVB, where the M is molarity, V is volume. So the A would be for the acid, the B is for the base. Now this was just like the dilution equation. M1V1 is equal to M2V2, but we're doing it with acids and bases. All right, so let's do an example. It's super easy. Just keep the things together that go together. So this information here is for the hydrochloric acid. This is on the base. So we're trying to figure out the molarity. So 54.6 milliliters of the 5.0 molar is equal to 100 milliliters of what concentration? Very simple. 2 sig figs from my 5.0 molar. And that's that, okay? Because you have a 1-to-1 ratio when you balance the equation. You will not always have a 1-to-1 relationship when you're doing this. For example, in the next one, you've got magnesium hydroxide reacting with hydrofluoric acid to give me H2O and magnesium fluoride. So that's a 2, and this is a 2. So we are in, it's not a 1-to-1 ratio. So what we're going to do is we're going to put the coefficient multiplier with the concentration. What I mean by that. So 22.8 milliliters of a 0.1 molar magnesium hydroxide. That's my 1, so I don't need to worry about it. I'm just going to do 22.8 milliliters, 0.12 molar. And then I have 10 milliliters of hydrofluoric acid. I want to know what the concentration is. So I'm going to put 10.0 milliliters times 2x. I'm putting the coefficient of the multiplier with the concentration, which in this case happens to be x because I'm going to solve for it. When you solve and do this, 2x is 0.27 molar. X will be 0.14 molar. So that will be the concentration of the hydrofluoric acid. That's it. Okay, so the only thing about titration calculations that you want to pay attention to is if you have a multiplier or not. So let's look at a titration curve and answer some questions based on it. So pH of an unknown acid versus the volume of sodium hydroxide. So we've got pH of the unknown acid, the volume of the 0.1 molar sodium hydroxide. You can see the pH steadily increases until you've got your big bump, and boom, you get your equivalence point. So what's the Ka? So remember, the Ka for this acid is equal to the pKa. No, wait, no. Ugh. Blah, 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 blah. So remember, pH is equal to the pKa at the half equivalence point. So the pKa is 4.2 because this is my half equivalence point. And therefore, remember, pKa is the negative log of the Ka. And so if I did this math, 4.2 is equal to the negative log of x. So the Ka is equal to 10 raised to the negative 4.2. And I'm sorry, I'm just doing all of the steps. I don't think you care about how the math works. 6.3 times 10 to the negative fifth. So your Ka will be equal to 10 raised to the negative pKa. You can write that down. That's a good equation to have. And then we want to know what is the molarity of the unknown acid if 12 milliliters of acid was used. Okay, well, at the equivalence point, I use 19 milliliters of my base. And I know that that base is 0.100 molar. If I used 12 milliliters of acid, what was my concentration? And X would just be 0.16 molar. That's it. Okay, so indicators are substances that react with the hydronium or hydroxide ions that become an acid or base in response. This makes the substance change colors at certain points. So like I said, phenolphthalein is the one that we use, going from colorless to a red. So let's do some questions where we calculate the pH of a solution during a titration of 25 milliliters of a 0.25 molar sodium hydroxide with 0.5 molar hydrochloric acid. Let's do the last question first. How many milliliters of hydrochloric acid are needed at the equivalence point? Okay, so we're going to do 25 milliliters of the 0.25 molar sodium hydroxide is equal to how many milliliters of the 0.50 molar? X will be equal to 12.5 milliliters at the equivalence point. Boom. Okay. So if we want to determine the pH at different points along our titration curve, we want to think about moles. So if we think about it in terms of moles, it makes it a lot easier. So starting off, I start with 25 milliliters of a 0.25 molar solution. How many moles is that? 0.25 molar times 0.025 liters gives me 6.25 times 10 to the negative third moles of the hydroxide ion. Okay, boom. Because remember, what's happening, that's how much hydroxide I start with. I'm adding acid to neutralize it. So let's see how many moles of acid we add. So at 0.50 molar times 0.010 liters gives me 5 times 10 to the negative third moles of the H plus. So what remains after I add that? What do I have left? Whatever I have left is the thing that's giving me my pH. And so in this case, if I take 6.25 times 10 to the negative third, and I subtract 5 times 10 to the negative third, this would be the moles of the H plus. No, that's the OH minus, excuse me. That will give me 1.25 times 10 to the negative third moles of H plus after that. Well, remember, pH is the negative log of the H plus concentration. So now, what's my total volume? I started with 25 milliliters. I'm adding 10 milliliters. So it is 35 milliliters. And so this concentration will be 0.036 molar. And so then I will calculate the pH. So .44. Nope, I'm sorry. I'm looking at the wrong thing. Oh, I'm so stupid. Oh, yes, I am so stupid. Because I have the hydroxide was winning. What am I doing? Sorry. Duh, this is more. So that's hydroxide. So that would be the POH. So the POH equals 1.44. And the pH would be 12.56, which makes sense because I'm starting with base and slowly adding the acid. Sorry, boom, so bad for that. But the idea, determine the moles. What do you have left after they've neutralized each other? Determine that concentration, calculate the pH or POH in order to get that. So at 50 milliliters, I know I'm past my equivalence point because it took 12.5 milliliters to get me to my equivalence point. So if I use 50 milliliters of hydrochloric acid, that's going to be 0.50 molar times 0.050 liters, which gives me 2.5 times 10 to the negative second moles of H plus. Okay. So I'm definitely going to have hydrogen ions at the end of this. So I'm going to take the difference between the two. 6.25 times 10 to the negative third moles of the OH minus. So that's how many moles I have. I'm going to now divide it by 50, 60, so that's 75 milliliters as my total volume now, which gives me 0.25 molar, and therefore my pH would give me 0.60. Okay. So when you're doing a titration question that's not asking you about the equivalence point, it's asking you to determine the pH at various times. You want to do it in terms of moles. Determine how many moles you start with, determine how many moles of the other thing you're adding. Whichever wins is the one that's giving you your pH, okay? So if you have any questions about this, because that's it, if you have any questions about this, please make sure you ask them in class. Work on your homework assignment. Okay, again, titration calculations, not difficult, but it's one of those pivotal things in this class. and work on that simulation. Okay, I will see you later.